Okay, this is the second part of this two-part series on energy disaggregation. In the first lecture, we talked generally about what that means, going from sort of a global view of what sectors contribute to electricity consumption, how that changes seasonally and even hourly, but then disaggregating that down first onto the household level. And there's a number of ways you can sort of do that. The EIA tries to estimate what types of energy consumption is coming from different households throughout the United States. But then we're really interested in trying to bore down even into more detail about what individual devices are contributing to electricity consumption and how that varies through time. Smart meters, again, are reaching this point at which they are very, very widespread in terms of their adoption throughout the United States. About 43%, it's more now, closer to 50% of households in the United States have smart meters. And what that gives utilities is a load signal from individual households so they can tell how your electricity consumption is changing throughout the day on a minute-to-minute and hour-to-hour basis. The trick is, what we really want to do is have an idea of what individual devices in the home are causing those specific dynamics. There would be a number of advantages to knowing that information, whether it's being able to more accurately target energy efficiency programs or demand response programs, or empower individual consumers to make more deliberate decisions or automate devices through some sort of energy management software about how and when they're using their electrical devices. Now the problem is to disaggregate smart meter data, which into the device level. The standard approach has been to install plugs on individual major appliances, and that can be pretty expensive because they can cost $50 a pop. So if you have 10 major appliances in your home and you're using a $50 plug on each one, in order to send a utility specific information about electricity consumption for each device, that's really expensive. And so what we want to do is find a way to accurately report what electricity consumption is coming from each device in the home without having to install hardware. And so that was served as a segue into this introduction of non-intrusive load monitoring, which is this family of analytic approaches aimed to do just that. On the household level, given a smart meter at the household that can report to the utility minute-to-minute and hourly electricity consumption as a whole for the whole house, these analytic approaches facilitate disaggregating that into device-level data without actually having plugs installed on devices and appliances in the home. And so we're going to go through what this means, and this is a rapidly growing field and one that's becoming increasingly complex and sophisticated. And so I'm going to give an example of sort of the first most famous approach that was tried, but know that we're just going to be sort of scratching the surface today. So this is a figure or series of figures that I showed in the last lecture. So on the left, it represents the total power consumption for a particular household over about 40 minutes. And obviously this is a very dynamic signal, and this blue signal is what the utility would see coming from a household with a smart meter in place, right? So the smart meter is able to communicate this blue signal back to the utility, and what we really want to do is break that blue signal up into its component pieces, in particular to disaggregate it into the individual devices that are being used when. That means to know during what part of this 30 or 40 minute period the kitchen outlets are being used versus the microwave versus the washer dryer, etc. And again, this is an analytic approach, so it is an alternative to high-priced traditional submetering that requires individual plugs on every major appliance. And so the upside of this is to get the same amount of information that you would have, the same accuracy of information that you would have with devices on every appliance in every house, with an algorithm, with a computer algorithm basically, that is easy to implement and cost effective, and provides just as many benefits in terms of increased information flow, as having actual plugs on devices that you would need to help facilitate programs for energy conservation, efficiency, and demand response. So the general approach I'm going to lay out for sort of traditional non-intrusive load monitoring is as follows. First, there's a signal acquisition, and that just means installing a smart meter and having the ability to get that blue signal that's not disaggregated. Feature extraction involves pulling out features or patterns in the load measurement data that then you are using to identify individual appliances within the data and make a guess about how they are being turned on and off throughout the time series. And then number 3 is the actual appliance classification, which requires analyzing the extracted features to discern appliance level specific load from the whole building data. So again, signal acquisition is just having, in this case, a smart meter in place, so the ability to get this two-way communication of data that would come from the household to the utility. And what we want to do is disaggregate this into individual appliance level data. So the second step after you have this signal from a smart meter is to try to pull out from that data individual patterns or features of that data that correspond to specific appliances. And there are a number of different general approaches for doing this. There's steady state, there's transient, there's harmonic approaches, there's sort of hybrid approaches. And I'm just going to talk briefly about transient, but really just focus on steady state because I think it's the easiest to wrap your head around. So both approaches are really looking at, they're looking at a time series of electricity consumption for the household level, and it's all about identifying changes, changes in the operation or in the electricity demand signal that correspond to when an appliance goes from one operational state or level to another. So that could be on and off, that could be low to medium to high, etc. Now the steady state signature is really sort of the beginning of non-intrusive load monitoring. It's one of the most widely used signatures in the academic literature. And so that's really talking about step changes in active or reactive power, and we'll talk about the difference between those two if you're not familiar with that. And so it works really well on devices that you turn on and off, and devices that have very discrete levels of operation like low, medium, and high. So that could be water heaters, air conditioners, etc. This is not as useful for devices that require fast sampling data, and we'll talk about what some of those would be. So here you have a figure. On the y-axis you have power consumption, and on the x-axis you have time. And each of one of those dots is a sample or a measurement, for example, from your smart meter, right? So your smart meter is maybe not reading constant electricity output, it's taking samples, right, every 5 minutes or something like that. So each dot is a different interval in time. And so what it is tracking is power consumption at each interval. And so what an event-based algorithm for non-intrusive load monitoring does is it looks for discrete on and off points or jumps from low to medium to high. And so what that means is what we call step changes in power consumption. So the step changes here that are pictured are represented by these black arrows. And the first one, you see there's a sort of steady state power consumption, and then you see this increase from one period to the next that represents in this case a device being turned on, and then that state continues for several time periods until some other device is turned off. Now notice that the second steady state that we see here doesn't drop back down to the original. What that suggests to you is that there was some device turned on in the first steps change and a different device was turned off, or the device that was turned off was not turned completely off. It went from high to medium, or medium to low, or something like that. And so what we're really looking for is being able to quantify in each case all of these events, these black arrows that represent step changes. And what we want to account for is some tolerance in what those steady states are. You can sort of see what look to be confidence intervals around each steady state. So you have sort of a line of best fit around the black dots, and then little dotted lines on either side. And so in that case, what we're doing is we're saying, there can be some minor variation in power consumption at a steady state where we still sort of consider it at that one state. So we allow for those sort of minor fluctuations. What we're really interested in are the really big jumps up and down. So that's steady state. In transient appliance signatures is a little more complicated. It refers to the shape, duration, size, and harmonics or frequencies of transient power fluctuations of different types of appliances. And so this is really looking at the specific characteristics of individual appliances in terms of the frequencies at which they operate. Especially when they're turning, and some of the responses of those devices when they're being turned on and off. And so this is, it's more complicated than the steady state based approaches. And I actually know a little bit less about this stuff than the steady state stuff. So we're not going to spend a lot of time on it in this lecture. But here's an example of a transient voltage signature. So in both cases you have time on the y-axis and frequency on the x-axis. So these different devices have different frequency signatures. And so what you're really looking for are changes in color, because the changes in color represent changes in amplitude or voltage at each frequency. So each place on the x-axis is generally associated with a different device, and you can see in a lot of cases these figures identify the different frequencies at which all these individual devices are operating. And then their color represents the amplitude of the voltage. And now when you notice changes in the color, that indicates a device being turned on and off. And you can see CFL lamps being turned on and off, two different CFL lamps at different frequencies, TV turning on, washer turning on and off, etc. And so this is, in a lot of cases, a more precise way of differentiating between different types of devices that may have pretty similar sort of steady state signatures if we're talking about their real power consumption. And so this is a way of, a more sophisticated way of differentiating between a lot of devices that don't, or between devices that don't have as clear sort of on and off and different operational levels associated with them. So the third step in this general framework for non-intrusive load monitoring is appliance classification. So after we got the signal from a smart meter, we pull out the useful information. In this case, we're really looking at changes in the signal, whether it's based on devices' frequencies or their steady state power consumption. Then we're trying to take that extracted data and really match it up with individual appliance data. And so in that case, we're really relying on having sort of an existing library or database of whether it's real and reactive power consumption for different devices, or their transient signatures in terms of their voltage or frequency. So in this case, we're really talking about algorithms that we're categorizing them generally as event-based or non-event-based, and we're just going to talk about event-based stuff. And so that really refers to approaches that rely on edge detection. So changes, right? So if we're thinking about a time series, an edge detection would be, in the case of a steady state signature, then we're looking for parts of the time series that make really big jumps, right? Go from a 1 to 0, and if we're talking about a device turning on and off, and then those extracted features are then classified using some sort of supervised machine learning algorithm, which means we have some sort of training data set, a library of devices that we know have certain levels of real reactive power associated with them, and then we're matching that, trying to minimize the error of matching that with the features that we extracted right from the smart meter data. So if we're going to do an event-based classification where we are taking a signal from smart meter data, extracting the features, matching those features with the power consumption of known power consumption of different appliances, and then using that to estimate based on this signal on the left here, sort of fill that in and estimate what devices are being used at what times. That is this, we're talking about supervised machine learning, which requires us to have a database of devices already in place, and knowledge of what levels of power consumption are associated with all those different devices. And the way you do that is by making an investment in plug level load monitoring. So you would have to, in some cases, in order to build this library, you may have to have a series of sort of test houses where you do install plugs on all these different devices in order to understand how they're used within a household and how much power consumption they actually or what levels of power consumption they're associated with, whether it's whether it's as simple as them just being turned on and off, or whether they're fluctuating or going from different levels throughout the cycle of a device's use. For example, if you're talking about a dishwasher or a clothes washer, they may use different levels of electricity at different times during one complete cycle. And so in order to do that, what you really want to do is have some ability to have accurate monitoring data, in particular time series of total household electricity demand here on the left, and be able to match that 100% accurately to a time series of correctly disaggregated electricity demand. And the way you would do that is by actually installing plugs on each device. And so this is how you would build a library. And in some cases you might be able to get some information from manufacturers, but I think in that case you're sort of running the risk of devices not working exactly as, the information about the power consumption of different devices not being strictly accurate when it comes to what's written on the appliances themselves, or the information that comes with them. And so the only way to really do it is to install plugs. And so once you do that for enough houses, for enough different devices, then you have this more robust library that you can use to match to extracted features later on that you pull out of smart meter data. So if we assume that a library of device level data exists, then and you want to go through smart meter data and try to disaggregate it, the first step is to come up with some sort of edge detector algorithm that identifies changes in steady states. And so all of this is coming from sort of the seminal net intrusive, or non-intrusive load monitoring study that was written by a guy named George Hart in 1989. So this field is pretty old, more than 25 years old. But it's obviously advanced quite a bit beyond this. And so what I'm going to show you today is really the first most important non-intrusive load monitoring technique. And I'm hoping you will realize that the field has advanced quite a bit beyond this today. So let's say we have this total power signature that's shown in this blue diagram over on the top left. And what we really want to do is go through this and have an algorithm that identifies anytime we experience a step change. And that's sort of zoomed in here in the figure in the bottom right. So step change we're defining here as any sort of increase or decrease beyond a certain threshold, right? And the threshold here are what looks to be our confidence bounds around what we are saying is a steady state. So we're going to realize that, or assume that there's some variation around the steady state, and we want to build in some tolerance for that variation, so we're not identifying these little tiny changes as step changes and then going and looking for devices that are associated with power changes of those size. We just are interested in with these really big changes, and so we have to build in some tolerance, some threshold of change that would qualify in the algorithm as an event or an edge or step change. So if we go through a whole time series, and every time we come to an edge, whether that's an increase or a decrease, we record it, and then we can cluster these, right? So if you guys remember k-means or geometric clustering, that's sort of like plotting, information in 2 dimensions in a coordinate system, and then using a separate algorithm to group those into or put those into groups in a way that minimizes the total distance from the centroid of each of these individual groups to all the members of each group, right? So in other words, it's coming up with the best way to group these in terms of the x and y variable. Those are the main criteria for grouping these, and you could in theory classify them or cluster them in as many dimensions as you want if you had information not only about real and reactive power, but some other device level data. You could cluster them in 3 dimensions if you wanted to. So in this case, this is all information that we pull directly from the smart meter level data. And so on the previous figure, I only showed you a time series of real power consumption. For a lot of these, for household devices, we have to classify them in terms of both real and reactive power. So most loads or devices that use electricity are associated with some level of resistance, but also other aspects of circuit behavior, including inductance and capacitance. And so because you have some potential for inductance and capacitance, which is associated with non-resistive load, so anything other than a light bulb basically, you have some potential for reactive power. And so I'll go into some detail about the difference between these two. But the main upshot here is that we are characterizing devices in terms of 2 dimensions here, real and reactive power. So remember, we have AC power systems, so the electricity coming out of our outlets is also alternating current. And so if a load is purely resistive, and that could be incandescent light bulbs, or a heating element in your oven or stove top, then the voltage and the current are completely in sync, right? So they reverse their polarity at the exact same time, and every time, so that means that at any time point, multiplying current times voltage gives you at least a positive number or 0. And so as a result, only what we call active power, power that can actually do work, is produced. So examples of, again, are incandescent light bulbs, so light bulbs that are purely resistive, and then toasters, ovens, stoves, etc. Right. So basically, anytime you're turning electricity into heat. Now, when there are other devices that are associated with some level of inductance or capacitance, then what happens is the voltage and the current, their waveforms don't line up perfectly. And so when you multiply them, you can get negative numbers. So reactive power is created by some delay between the voltage and the current. And reactive power is created along with real power, except reactive power cannot do useful work. So if the loads are purely reactive, then that means that the voltage and the current are 90 degrees out of phase. And so for half of each waveform cycle, the product multiplying V times I is positive, but on the other half, the product is negative, so that on average, just as much energy flows towards the load of the device you're using as actually flows from the device back onto the circuit. So the whole point of that, the description of real and reactive power, is to give you some idea of what reactive power is, and we quantify it in terms of VARs as opposed to watts for real power. And so different devices are associated with different levels of real and reactive power. Again, I mentioned the purely resistive loads, so like lights or incandescent lights, heating elements, and toasters and ovens are associated with purely resistive loads, so they don't have any reactive power, they're just real power. So they would be somewhere here on the x-axis. And actually, I think you can see one example of that at 500 and minus 500 in terms of real power. That must be some sort of purely resistive load, probably an oven. Everything else is associated with some level of real and reactive power. And so we use a two-dimensional geometric clustering here to put all these into groups. And so all these different dots, you shouldn't interpret this as these individual dots being individual devices. Remember, these dots are all coming from our assessment of this time series and identifying step changes or edges or events that occur in the time series, and we're recording that information. And so what you should sort of gather from this is that if you're drawing a diagonal line from the top left quadrant to the bottom right quadrant that goes right through the origin, 0, then this is sort of a symmetrical graph, right? You should see, both blue circles are sort of like equidistant from the origin, and the red circles are equidistant from the origin, and the green circles as well. And what that tells you is that each individual circle is sort of a device, right? And when it's in the top right corner, that means the device is being turned on. That's the information that we're pulling from the time series. Is the orange circle is any time that a device that with real power of 500 watts and reactive power of 200 watts is being turned on. And in the bottom left quadrant, the same dots in the orange circle are now associated with a drop in real power of 500 and a drop of reactive power of 200, and that's that same device being turned off. And so if we have a library, whether it's because we have an extensive sample of houses that we've installed with actual device level plugs to understand what devices are associated with different levels of consumption of real and reactive power or something else, then we can match those individual clusters actually to specific devices. And so this is an example. it sort of gives you an idea of this would sort of be like the top right quadrant of that figure I just showed you. And so this, you could get some of this information from the manufacturers of these devices, or it could be the result of direct experimentation by installing plugs on each of these devices. But you can see that we can sort of assign levels of real and reactive power to each of these devices. And with some wiggle room, right? There's going to be some variability in the real power consumption of a dehumidifier, right? It's less variable in terms of what reactive power it consumes, but there's a range, right? And so what we hope is that these individual devices are spread throughout this space sufficiently that if we see the features show up in time series data, we can sort of unequivocally say that that's what's being used. We can actually go one step further if we want to. We can characterize devices in terms of their real and reactive power, but we could also characterize them in terms of their on and off duration. And again, that would have to be something that does come directly from experimental data by putting devices or plugs on individual people's homes. This is not something that a manufacturer would be able to tell you, because obviously it would be pretty conditional on how individual people use their electrical devices. So then we design an algorithm, right? So we have this total power signal on the left, and we're extracting all the events. Events being any time where we see a step change in power consumption, whether that means going up or going down. And then when we see that something go up or go down, we go to this library of devices that we have, and we say, okay, anytime it goes up by 500 watts, that could be 100 light bulbs, or it could be an oven turning on or something like that. And so we design an algorithm to go through the total signal, identify events and step changes, and then search through the library for an appliance that's closest in both categories. In terms of power usage, usage duration, etc. And then ultimately, in order to test the accuracy of the algorithm, we compare the estimates of what we assigned to what was actually measured, right? So we want to have some ability to quantify the accuracy of the algorithm that we came up with. And here in this case, there's some level of obscurity in terms of being able to identify really what devices are being used at really low load levels or power consumption levels. So there's a significant part of the bottom of the left figure that's unassigned, which means we don't have an idea what's going on there. But we do have a better idea of, for example, when kitchen outlets are used, and when the washer dryer is used, and when the microwave is used. What's a little harder to do is to try to understand electronics. But this is a pretty accurate estimation of actual appliance usage. The left and right figure here match up pretty well. So there are other, I mentioned, this is a really simple example using the event-based steady state approach. There's a lot of, and just using the supervised machine learning, right? Having a database of, device characteristics, whether that's in terms of real reactive power or, on and off duration. This field is advanced well beyond that, and now uses a lot of unsupervised. It's trying to move towards unsupervised machine learning, where this would sort of obviate the need for a library of devices, right? They would just use input data from smart meters and using hidden Markov models or other, artificial intelligence or machine learning algorithms to estimate device electricity device or device consumption of electricity without having this having to go through this process of like installing plugs and coming up with a library, right? And that's the the labor intensive part of this whole thing is coming up with the knowledge base or the database of what types of appliances use what. And once you have that, doing the supervised machine learning stuff is pretty easy. But there are a lot of other approaches for doing this, and you can sort of make it as sophisticated and as complicated as you want. But I am not an expert on any of that stuff, so I think if you're curious, there's a lot of literature out there that you can investigate. Okay, here are the references I use for that. I hope this makes sense. We're going to do an example in class, sort of an easy example of non-intrusive load monitoring. But I hope this discussion of energy disaggregation and this approach was interesting. It's definitely probably the most machine learning type approach we're going to look at in this class, and I think it really relies heavily on computer science knowledge. The people that are advancing this field are much more into computer science and algorithms than they are into energy and engineering and stuff like that. But it's really cool, and it can make a big difference down the line.